Lecture 4, Describing Data, Displaying and Exploring Data. In this section, we're going to be looking at skewness. Of course, this is another characteristic of the shape of our data set. So, as we've seen before, there's several descriptions of what the skew may look like. 1, data is symmetrical. 2, it is positively skewed. And 3, it is negatively skewed. We've seen, based on a graphical representation, what this looks like. But in this section, we're going to quantify. The coefficient of skewness that we're going to be looking at is called the Pearson Coefficient of Skewness. And it ranges from a value of -3 up to +3. If you get a measure of skewness of -3, we have a very considerable negative skew. A value of +3 indicates a considerable positive skew. A value such as 1.63 indicates moderate positive skewness. And if you get a value of 0 for your skewness coefficient, then your data is perfectly symmetrical. So let's look at the equation for the coefficient of skewness. So the skew of a distribution is equal to 3 times the mean, x bar, minus the median, divided by the standard deviation of the distribution. If we were to look at pictures of skew, positively skewed distribution has a tail that is elongated on the right side of the data set. A negative skew is elongated on the left side of the distribution. So let's do an example. Here is earnings per share for a sample of 15 software companies for the year 2007. The earnings per share in this case are organized from smallest to largest or in ascending order. In order to figure out the skewness, we need the following information. We need the mean, we need the median, and we need the standard deviation in order to get to the Pearson estimate for skewness. Let's start with the mean. If we add up all of our observations and divide by 15, the total number of observations, we get a mean of 4.95. The standard deviation of this distribution is $5.22. The median, the middle value of the set of data, is 3.18. When we plug all this information into the equation, we find that the skewness coefficient is 1.017, which indicates that there is a slight positive skew in our data set. Numerical measures of relative standing. So in this chapter, we're going to be looking at locations of percentile. Before I go into the details here, I want you guys to think about one thing. I want you to think back on the standardized exams that you guys took in high school. The results of these standardized exams were typically written to you in the form of percentiles, not necessarily in terms of how many questions you guys got wrong or right. However, it would give you information in terms of how you ranked relative to your classmates. So if you, for example, ranked in the 80th percentile, what that meant was that 80% of your classmates did worse than you, and 20% of your classmates did better than you. If you ranked in the 90th percentile, 90% of students did worse than you, and 10% of students did better than you. So one key criteria of this breakdown is to divide data into quartiles. When we divide data into quartiles, we divide it into 4 exact equal parts. The first quartile designates the first 25% of the data. The second quartile would show us the first 50% of data. And the third quartile would show us the first 75% of your data. Further, we can break down the data into deciles, which is breaking them into 10, right? Dividing your data into 10 parts. So the 8th decile would represent the 80th percentile. If we break your data into percentiles, we're breaking it down into 100 equal parts. So for example, if we're talking about the 99th percentile, we're talking about the bottom 99% of observations. So standard deviation is the most commonly used measure of dispersion. Alternative ways of describing spread of data include determining the location of values that divide a data set into equal parts. These measures include quartiles, deciles, percentiles. To formalize the computation procedure, let's refer to LP as the location of the desired percentile. So if we want to find the 33rd percentile, we would use L33. If we want the 50th percentile, we'd use L of 50. This location is basically telling us exactly where to find those specific percentiles P's relative to the data set. The location of percentile equation is found by taking n plus 1, which is the number of observations plus 1, times the percentage we're looking for, P, divided by 100. How do we interpret this percentile? So for example, a test score in and of itself is usually difficult to interpret. For example, if you learned that you scored on a measure of shyness was 35 out of 50, you would have little idea of how shy you are compared to other people. More relevant is the percentage of people with a lower shyness score than yours. So this percentage is called the percentile. So if 65% of the scores were below yours, then you would be in the 65th percentile, which would mean that 65% of people were more shy than you were. Let's do an example where we will be using our location of percentile equation. Let's do an example with this data. So listed below are commissions earned last month by a sample of 15 brokers at Salomon Smith Barney's in Oakland, California office. So first thing we're going to do is we're going to organize the data from lowest to largest, and then we're going to take this data and find all of our different locations of percentile. Here's our example. So listed below are the commissions earned last month by a sample of 15 brokers at Salomon Brothers Smith Barney's in Oakland, California. So this data is now in ascending order, so we can use it to find our locations of percentile. So let's start this example. So first thing we want to do is we want to find the first quartile of this data set. Okay, so to find the first quartile, that represents 25th percentile, and the 25th percentile can be represented by L of 25. So let's find the location. So in this case, we have 15 observations. So our location of percentile equation is n plus 1 times P, which in this case is 25 over 100. So L of 25 is going to be 15 plus 1 divided by 25 over 100, or basically 16 divided by 4, which is 4. So what does this tell us? This tells us that the location of the 25th percentile, or the first quartile, is the 4th observation. So let's count. Observation 1, 2, 3, and 4. So what is quartile 1? Quartile 1 is equal to 1721. Now let's find quartile 2. Quartile 2 is going to be the 50th percentile, the midpoint of our distribution. So let's find L of 50. L of 50 is going to be 15 plus 1 times 50 over 100. So we have 16 divided by 2. So L of 50 is equal to the 8th observation. So that's so we have 4th, 5th, 6th, 7th, and 8th. So quartile 2, or the median of this distribution, is 2038. Next, let's find quartile 3, which is the 75th percentile. So L of 75 is 15 plus 1 times 75 or over 100. which is equal to 12. So the 12th observation in this data set is the third quartile. So we have 8, 9, 10, 11, 12. So quartile 3 is equal to $2,205. Now, that would be all of the findings for this specific data set. In this case, we had an odd number of observations, so our process was fairly straightforward. When we have an even number of observations, we have some complications in the process of finding the different quartiles. In the previous example, the flocation formula yielded a whole number. What if we had an even number of observations? So in this sample, we're going to be looking for the first quartile, the second quartile, and third quartile in the case where we have an even number of observations. Let's see what happens. Here's another data set. In this case, this data set has 1, 2, 3, 4, 5, 6 observations. Let's find the first quartile of this data set. So Q1 is equal to the 25th percentile, so L of 25. L of 25 is 6 plus 1 times 25 over 100. In this case, the first quartile is going to be at the position of 1.75. What does that mean? It means we're going to the first value and about 75% of the way between the first and second observation. So that means that quartile 1 is going to be somewhere in between 43 and 61. Particularly, it's going to be 75% of the way between 43 and 61. Let's find out what that means. So in order to get to that number, the first thing that we're going to do is we're going to do the following. We need to find what is 75% of the way between 43 and 61. So let's find that. So in order to find that, we take 0.75 and we find the gap between 43 and 61. And what do we find in that case? We find 13.5. So in order to find that first quartile, we take 43 plus 13.5 and find that the first quartile is in fact 56.5. So this will be Q1. Now let's find Q2. Q2 is going to be L of 50. So we have 6 plus 1 plus 50 over 100. Okay, so this is going to be 3.5. So this is the 3.5th location. So if we go back here, we have 1, 2, 3.5. So the second quartile is between 75 and 91. How do we get that value? For that, we take 75 plus 0.5, which is 50% of the way between 91 and 75, and we find that Q2 is equal to 83. So 83 is the median of this data set. What about the third quartile in this case, Q3? Q3 is going to be found by 6 plus 1 times 75 over 100, which is equal to position 5.25. So what is the value at position 5.25? So we have 1, 2, 3, 4, 5, and this is 6. So 5.25 is going to be somewhere here. So let's find where that is exactly. So Q3 is equal to 101 plus 0.25, so 25% over the way between 104 and 101. What is that Q3 number equal to? That value is equal to 101.75, and this is going to be Q3. The next type of graphical representation we're going to be looking at is a box plot. And a box plot is based on our quartiles. So to construct a box plot, we need 5 statistics. We need the minimum value, we need the first quartile, the median, the third quartile, and the maximum value. So let's start with step 1. Step 1 is to create an appropriate scale along the horizontal axes. Step 2 is to draw a box plot that starts with Q1 and ends with Q3. Inside the box, we have a vertical line to represent the median. Then we extend horizontal lines from the box out of the minimum value and out to the maximum value if we don't have outliers. However, if we have outliers, the box plot may have different whisker points or endpoints. Here's an example. Alexander's Pizza offers free delivery to its pizza within 15 miles. Alex, the owner, wants some information on the time it takes to deliver a pizza. How long does a typical delivery take? And within what range of times will most deliveries be completed? For a sample of 20 deliveries, here's what was determined. The minimum value was 13 minutes. Quartile 1 was 15 minutes. The median was 18. Q3 was 22, and the maximum was 30. If we were to develop a box plot with this material, assuming that there was no outliers, here is the box plot we would see. Notice that the whiskers, or the endpoints of the box plot in this case, are the minimum and maximum value in the data set. The box itself is constrained by Q1 and Q3. And of course, we have to mark the median of our data set as well. The next step is to look at how we detect outliers. An outlier is an observation that is unusually large or small relative to the other values in the data set. Outliers are typically attributed to one of the following. The measurement is recorded or entered incorrectly. The measurement is very different than the population, or comes from a different population, and the measurement is correct but represents some kind of very low probability or chance event. One definition: the interquartile range, or IQR, is the distance between the upper quartile and the lower quartile. The upper quartile is the third quartile and the lower quartile is the first quartile. So let's look at this equation. A value is an outlier if, let's look at a positive outlier. A positive outlier would be a value that is greater than value of the third quartile plus 1.5 times the interquartile range. A value is a small outlier if it is less than Q1 minus 1.5 times the interquartile range. How do we use a box plot to detect outliers? Well, first, we have to create an appropriate scale. Second, we draw a box that starts at Q1 and ends at Q3. Then we extend the horizontal lines of the box out to the lowest datum, still within 1.5 IQR of the lower quartile, and the highest datum, still within 1.5 IQR of the upper quartile. If we look at this data set here, or these box plots, what we notice here is we have time to complete something, and we've divided the data set into gender, male and female. Now, the little point here, the dot, represents an outlier. This line here is the upper range, and this is the 1.5 times IQR above the third quartile, and this value here represents an outlier in our data set. Let's do a practice problem. Here is a data set. Let's test this data and see if we have any outliers, and then draw our box plot. Let's create a box plot with the data. So this data represents the heights in inches of students in a statistics class. So first thing we need to do here is we need to figure out what is the median, the first quartile, and the third quartile. So let's start with the median. So this is going to be Q2. We have 20 observations, so the location of Q2 is 20 plus 1 times 50 over 100. So Q2 is 21 divided by 2, which equals 10.5. So let's count it out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the median is somewhere between 63 and 64. It's halfway between them. So without doing any work here, the median is in fact 63.5. So there's our first point. Now let's find Q1, which is the first quartile. Q1 can be found by taking 20 plus 1 times 25 over 100, which is in fact 21 divided by 4, which equals 5.25. Let's find that observation. So we have 1, 2, 3, 4, 5. So this is going to be 25% of the way between 56 and 59. Let's find what that means. So 25% of the way between 56 and 59 is going to be found in the following way. We have 56 plus 0.25 times 59 minus 56. So that's going to be 56 plus 0.75 or 56.75. This is going to be Q1. Now let's also find Q3, and we are all set for our box plot. Q3 is going to be what location? So we have 20 plus 1 times 75 over 100, which equals 15.75. So it's the 15.75th observation. So the 15.75th observation is going to be between the values of 70 and 71. So let's find what that means. So we have 70 plus 0.75 times 71 minus 70. So in this case, that's going to be 70.75 is going to be Q3. Now, before we draw our box plot, we need to test for outliers. Let's test for outliers in this case. So let's start with a large outlier. A value is a large outlier if we have the following. So large outlier if it is greater than Q3 plus 1.5 Q3 minus Q1. Q3 is 70.75 plus 1.5 times 70.75 minus Q1, which was 56.75. Let's see what a large outlier would be. So the upper limit of a large outlier would be 96.25. Now let's go to our data set above and see if we have a value greater than that. What we'll notice here is we have a value of 145, and this we would consider an outlier. Now let's check for small outliers. A small outlier is found using the lower limit, or the quartile 1. A small outlier is a value that is less than Q1 minus 1.5 times Q3 minus Q1. In this case, we have 56.75 minus 1.5, the interquartile range. A small outlier would be something less than 35.75. Going back to our data set above, we find our smallest observation is in fact 50, and therefore we do not have any small outliers. So let's create a box plot with our data set. So box plot. So what is our box plot going to look like? So let's say we start at 50 and we go in increments of 10. So 60, 70, 80, 90, 100, 110, 120, 130, 140, and 150. So first let's start with marking all of our observations. So let's find the minimum value. The minimum value in our data set is 50, so let's mark that as 50. And since we don't have a lower outlier, we can mark that as our starting point. Next, we need Q1. Q1, as we found, is 56.75, so there's Q1. Okay, now we need the median. As we found in our previous section, the median is 63.75, so we'll put it there. And then we also need Q3, which is 70.75. So here we have our box Q1, Q2, Q3, and now we need the upper limit of our data set, which is basically where we have an upper limit without our outliers, and that would be Q3 plus 1.5 times the interquartile range, which is equal to 96.25, which would be there. And this would be the upper limit of our range where we don't have outliers. And of course, an outlier in this case would be the value of 145, which is here. And in that case, we would just put a little star there to represent that. In this case would be our box plot. So this would be Q3 plus 1.5 times the interquartile range. But however, the one on this side, the minimum value would just be the minimum. And the reason is, since we don't have outliers, we don't have to label it as Q1 minus 1.5 times the interquartile range. So this is how we draw a general box plot. The last part of this chapter looks at describing relationships between two variables. When we study the relationship between two variables, we refer to the data as bivariate. One graphical technique to use to show the relationship between two variables is a scatter diagram or a scatter plot. To draw our scatter plot, we need two variables. We scale one variable along the x-axis and the other variable along the y-axis. Typically, the dependent variable goes on the y-axis and the independent variable on the x. What are some questions we ask? So first question we may ask is, does y increase with x? Does it decrease with x? Does it depend on what values? For example, it seems intuitive that weight increases with height, so taller people tend to weigh more. Suppose y does not increase with x. How fast does it increase with x? If you are 2 inches taller, how much heavier are you likely to weigh? Is the relationship strong? Can you make a reliable prediction? That is, if you tell me your weight, can I predict your height without seeing you? Or if you tell me your height, can I predict your weight? The relationship between the variables can be correlated, related, associated, etc. We can construct scatter plots to show the relationship. For variable 1 and variable 2, there's a positive relationship. So as variable 2 increases, variable 1 increases. In part B, we have a negative relationship. This states, as you increase variable 2, variable 1, which is the dependent variable, decreases. In this case, we can't really see a relationship, and therefore it is not clear. Let's have a look at some real examples. This first example is the age of a bus and the maintenance cost. But what do we notice here? We notice that the older a bus gets, the more expensive it is to maintain. So there's a positive relationship between the age of a bus and the maintenance cost. We have to use caution here. Correlation does not imply causality. If we think back to the example we had in our previous lecture, I think it was in lecture 1, we looked at a situation where we had misleading statistics, particularly the example about the number of churches and the amount of crime. We found that there was a positive correlation between the two variables. However, this correlation does not imply there was a causality. If you recall, we found that there was a third variable that impacted both, which was population. So in other words, your scatter plot may show a relationship exists, but it does not and cannot prove that one variable is causing the other. One other type of distribution we look at when we compare two levels of data, particularly when we're looking at nominal or ordinal level data, we look at a contingency table. A contingency table is a table used to classify observations according to two identifiable characteristics. First, a contingency table is a cross-tabulation that simultaneously summarizes two variables of interest. Specifically, students at a university are classified by gender and class, freshman, sophomore, junior, senior. Let's look at an example. So let's read this contingency table. There's a survey of 545 college students, and they were asked, what is your favorite winter sport and what type of college do you attend? Let's start with the first question. What is the probability or what is the possibility of selecting a student whose favorite sport is skiing? So in that case, we're looking at this column here, skiing column. We find out of all the students questioned, 171 of them liked skiing. So 171 out of 545 would give us the number of students who prefer skiing. Second, what is the probability of selecting a junior college student? In this case, we're looking at this junior college row. 155 out of the 545 were junior college students. And that would be the probability if we transform that into a decimal. 3. If a student is selected as a 4-year college student, what is the probability the student prefers ice skating? So we have a 4-year college student and we have ice skating, which is 70. So if a student is selected as a 4-year college student, we're really considering this specific row here. So 70 out of 210 are college students, 4-year college students that prefer ice skating. Okay, let's go on. If a student selected prefers snowboarding, what is the probability the student is a junior college student? Here's a snowboarder in this first column. So 68 of them are junior college students. So 68 out of 211 prefer snowboarding. 2. If graduate student is selected, what is the probability that the student prefers skiing or ice skating? So let's pick graduate students. So here's our row. 74 plus 47 like skiing or ice skating out of a total of 180. So the probability that a student prefers skiing or ice skating if they are a graduate student is 121 out of 180. That concludes lecture 4. So we will be looking more into details of this in our probability section in lecture 5.